great pleasure to introduce Mark Anton from CAUS. Mark, over to you.
Thank you. Thank you very much to IDRIS for the invitation and also other organizers. My understanding is that this week is a week on energy.
Yeah.
So my talk is going to be about energy, wind energy. And it's actually well suited because in my new university, King Abdullah University of Science and Technology, CAUS, you see that in the logo there are 4 seeds, and those 4 seeds represent 4 main research trusts of the university. One is water, the other is environment, food, and the last one, of course, is energy. Those are 4 topics very relevant for Saudi Arabia, but also in general to the world. And in addition, you see that those 4 seeds are linked together by bivariate density contours of a SKU-T distribution. So this is very, very appropriate. Even in the here it says SKU-T. And you'll see that I'll mention this a little bit later. So that was one reason for me to move to that new university. So so my talk is very related to the talk we had on Monday about wind energy also, about forecasting wind power. So I'll be talking about forecasting in the short term wind speed using spatial temporal information, also what is called geostrophic wind. And I'm also going to look at the effect of those forecasts on the power grid, on power system dispatch. So the presentation is a kind of overview. It involves work with several people. Xin Zhu is my former PhD student from Texas A&M. Ken Bowman was a colleague, a professor at Texas A&M in atmospheric science. And then Le Chier is an assistant professor of electrical and computational engineering at Texas A&M as well. And his student, Yijong Gu, also has participated in some of the research here. So here's the outline that I have for my presentation today. I want first to say a few words about CAUS because many people ask me about the university, and so I have a few slides about that. And then I'll go into the topic of wind power. I'll talk about motivation and challenges where I see that statisticians can be involved and maybe contribute in some way. Then I look at a data set from Texas because I moved from Texas to Saudi Arabia. So naturally I had data from Texas, so I'll talk about that. Then I look at some spatial temporal short-term wind speed forecasting models and present some ideas about that. And then what we want to do is to try to improve the prediction by introducing another quantity, which is called the geostrophic wind. And I'll talk about how we estimate this from pressure and temperature data. And so that's the first step. I mean, you can build all kinds of models to improve the forecast of wind speed and then wind power. But then the next question is, what's the effect really of those improvements in terms of running the power grid? And so another study here consisted in looking at power system dispatch. And finally, I'll end with some discussion and also opportunities maybe for interaction in the program here. Then there are some other topics I won't be able to talk about today, but I wanted to give you 2 previews because I think they are relevant to some of you as I had some interaction so far. And also at the very end, offline, I have a short movie about CAUS that takes 4 minutes. So for those of you who are interested, you can stay and watch the movie. So CAUS is a new university. It's a graduate level only university. There are no undergraduate students, only master and PhD. It's located about 50 miles north of Jeddah on the coast of the Red Sea. The campus is Western style, and it opened for the first classes in the fall of 2009. Currently, there are about 900 students and about 130 faculty, and it will remain fairly small, so it will grow to about 2,000 students and maybe 220 faculty, something like that. If you want to read more about it, just go to the website chaos.edu.sa and you will find a wealth of information and what is going on currently. So I got involved with this university through a partnership that Texas A&M had with KAUST. KAUST funded an institute, IMCS, the Institute for Applied Mathematics and Computational Science, and I got involved in that institute, and then with time I thought that it was a good idea to move there. So I'm recruiting students, postdocs, and also faculty. Currently I have a group of 4 postdocs and 4 students, and I think more faculty in statistics are going to join in the near future. So we have a new president also since July 1st of last year. Jean-Loup Chameau was the previous president of Caltech, so we're very excited to have him join and lead the university. So a little bit of geography. Here I have a map of Saudi Arabia with the Red Sea, the 2 holy cities of Mecca and Medina. Jeddah is here, and KAUST is just a little bit north of it, about 1 hour drive from Jeddah. So here's an image of the campus. Everybody lives on the campus. Those are the main academic buildings of the university, and then there are different communities. There's a golf course here, and a community of housing there. Another here. There's a harbor, the beacon, the symbol of the university, and all kinds of shops, restaurants, facilities, beach, whatever you want to live there comfortably on a daily basis. So here's another image of the main campus. This is the building to which I belong. This is the library, and the campus is, in my opinion, very beautiful with palm trees and very nice architecture. So this is a picture I've taken from the beacon, from the harbor, looking towards the academic building. There are beautiful sunsets because it's on the Red Sea and looking towards Egypt and Sudan. So in the evening you have those images. This is a picture taken from my backyard, looking at the Red Sea. And this is one taken from my office. So you see that often, especially in the winter time, there are a couple of clouds, and so the sky becomes very red. But of course, if you go in the sea, everything is blue. And the scuba diving is really amazing because there are essentially no tourists in Saudi Arabia, so the coast is untouched. So there's very good scuba diving. And this means that there are also many projects related to the Red Sea. In fact, there's a center that studies the Red Sea at KAUST, and there's a project about whale sharks where they tag and take samples and study whale sharks. They have tagged more than 100 whale sharks, so there are population size estimation problem with capture-recapture. There are tracking with satellites and so on. So there are many very interesting projects. So that's my very brief introduction to KAUST. So now what I want to do is to talk about wind power. So as we know, we have limited fossil fuel resources, and so getting energy from wind is an interesting concept because it's a renewable energy. Some people will say that it's green, but of course there may be some debate about that and effect on ecology and birds and so on, but I'm not going to enter in that discussion. What is interesting here is if you look at different countries in 2012, what was their share of energy that came from wind. Denmark had 30% of its energy coming from wind, Portugal 18%, and the US 3.5%. And in the US, there's an aggressive project to ramp this up to reach about 20% of the energy coming from wind by 2030.
There was something on the BBC News just yesterday saying that
okay.
the UK produces more, not as a percentage, but more in an absolute sense energy from wind than any other country in the world. Or maybe they actually said more than all other countries added together. Is that possible?
I'm not quite sure because I have the next slides is about some more detail about that. But, the point here is that I think it's a good idea to have this goal of increasing energy that comes from wind. But of course, this will come with some challenges. So it's not just, you cannot just increase wind power and just add it to the power grid like that. It means that maybe you need to change the power grid, or you need to think about how you're going to implement essentially the distribution of energy coming from wind in the power grid and balance it with other sources of energy. So it's a non-trivial problem. So here I have collected some information. On the left, you have a plot that represents vertically, you have the world total installed capacity in megawatts, starting from year 2000 up to 2012, and then the expected number for 2013, because the available data are up to June, first half of the year for 2013, and so this is an expected number, but you see that it started in 2000 with about 18,000 megawatt installed worldwide, and it has really increased very much, and now we're at about 380,000 is the expected number for 2013. And here you have a graph that shows a distribution by countries. So the country shares of this total installed wind power capacity in megawatts. So in blue is by the end of 2012, and the red one is the one by the end of June 2013. So you see that China is leading with 80,000 megawatts. So compare this to about 300 by June here, about 300,000. So a good force comes from China. The US with 60,000 installed. Germany, Spain, India, you see those numbers here. And then the UK is here at about 10,000. Italy, France, Canada, and Denmark. So those are the number I got recently. What is interesting also is that if you look at this chart in around 2005 or 2006, China essentially was not in the picture. So the US was leading in terms of installed capacity, but suddenly China has woken up on that and has aggressively developed energy coming from wind, and now it's really leading this source of energy. So Saudi Arabia has also some aggressive plans to try to change things. So there's a plan to have about 54 gigawatts, so 54,000 megawatts of new renewable energy by 2032. Of course, a lot will come from solar power, because it's very natural to use energy coming from the sun. In fact, it almost never rains. There are very few clouds, so it's sunny and blue sky most of the time. So KAUST has also a center for research on solar energy. So of course, there's a very big push in trying to develop this further. Here I know it's not very clear and you cannot see the detail, but essentially this kind of orangish are parts that will represent solar energy. And the wind part also, there will be some of it, about 9 gigawatt out of those 54 are planned to come from wind. And those are this green here that is planned to be developed. In fact, the wind situation is not bad. The potential is about 5 hours of full load wind per day on average, especially on the western coast where KAUST lies. You see that every afternoon the wind starts to pick up, and really in the afternoon it's windy. So I think there's a potential to develop wind energy on that coast as well. So what are the challenges with wind energy? Well, one of the challenges is to match the supply and the demand. The demand you can predict fairly reliably. I mean, it depends on time of the day and different factors. So this is not too much of a problem. But the electricity generated from wind, typically you cannot store it. And so you have to use it essentially immediately when it's produced. So because you cannot rely completely on wind, and there are days or times where there's no wind, you must supply the balance with other sources, such as nuclear power or coal or gas turbines or hydropower and so on. And so you have to balance all this with different costs and different time to reach, essentially to have those power plants online to produce electricity. You can have also penalties if you have excesses or shortages, depending on the type of utility. So the goal here is to try to predict the supply of electricity that will be generated from wind. And at short time horizon, typically 1 to 6 hours, statistical forecasts are very competitive. So this is why there's an interest in developing a simple statistical model, but to forecast in the short term. So this is what I'm going to consider. In addition, typically one would look at probabilistic forecasts, so you can also give information such as confidence interval or a full probabilistic distribution. In addition, you can think about if you want to predict wind speed so that you can predict wind power at a certain location, you can use information, historical data, essentially in time. So naturally, you would look at time series model. But you can also imagine intuitively that if you have information at other off-site location about the wind speed and maybe the wind direction, then this could be used to improve your forecast. So there's a spatial component also that naturally comes in here. So as I just said, the wind typically does not blow constantly, it's intermittent, and so it's difficult to predict. So sometimes you will have wind, sometimes a lot, and sometimes no wind. So if you want to integrate wind into your power system, essentially the challenge comes from those uncertainties from the supply side, so in that particular case from wind. And one possible solution is to come up with accurate forecast of wind speed and then wind power in the short term. And once you do that, you have to try to see what's the effect on introducing wind power in the power grid. So how do you optimize the power grid once you have certain forecast of how much power you can get from wind? So wind has some unique characteristic. So if you look at wind speed, for example, it's a non-negative quantity. Typically, its distribution is not Gaussian. You have correlation both in time and space. So as I said, at a certain location, if there's a lot of wind, then probably a little bit later, again, there will be some wind. You have correlation in time, but also correlation in space from nearby locations. So if you have another location where you know that you have a lot of wind and it's blowing in direction coming to you, then you know that this wind likely will come to your location. And so if you have that information, you can use it to improve your forecast. So it changes rapidly and with high frequency. And there is correlation, as I just mentioned, with the wind direction as well. So in fact, here I have a plot where I plot time horizontally in hours and vertically wind speed here in meter per second. And the black curve represents the wind speed. And I have overlaid on that plot wind direction by this blue dashed curve. And of course, the scale is not the same, but what you can notice is when you have a dip in the blue curve, here you have also low wind speed. So it suggests that there are certain direction of the wind that correlate with low wind speed.
But there should be increased uncertainty in the direction when the speed is low. It must be much harder to measure the direction.
Right. So there's a lot of variability in the wind speed and also the direction, but still it gives you some information that as we'll see can improve the forecast. But I think here there's room for all kind of model that could be developed and try to improve the existing practice here. But in fact, it's not that easy. I mean, you can try very sophisticated model, but it's not that easy to improve, to have a lot of improvement. So one difference, so here's a plot of the relationship between the power and the wind speed. One difference in my presentation compared to the presentation we had on Monday is that I will be focusing on predicting wind speed. So another option is to try to predict wind power directly. I think both have advantages and disadvantages. What I like about trying to predict wind speed is that then it does not depend on the wind farms or the type of turbine that you have at a certain location. So the wind farm could have different type of turbine that have different power curves, or you could add turbine that are different type, and it's really the wind speed that then you're interested in and will transform according to that wind power relationship. Another point that I'll mention later is that this is essentially an optimal relationship between wind speed and power that the manufacturer would give you. But in practice, there will be a lot of variability on this curve as well. So there's an additional step that one could consider, and that was discussed to some extent in the presentation on Monday, and I'll mention a little bit later on. But for now, I will assume that essentially this is the relationship between wind speed and wind power. Now, what is interesting here in that curve is that you see when the wind speed is low, essentially you produce nothing. Whether you have 0 wind speed or just 5, here it's in miles per hour, then there's no power. And then at this cut-in speed, the power starts to be produced, and it changes roughly as the cube of wind speed until it reaches a plateau, the maximum rated output of that particular wind turbine. And if the wind is too strong, then often you have to shut down the turbine, so you produce 0 again. So you have a very particular way of looking at the relation between wind speed and wind power. But if you can do some improvement on the prediction in this region where the power changes as the cube of wind speed, then the gain the potential for final gain are important. So let me say a little bit now about wind data in Texas. So Texas has the largest installed capacity of wind. You see a little bit more than 12,000 megawatts. Remember that the US now has 60,000 megawatts. So Texas in itself has a bit more than a sixth of that, which makes sense because it's a large state. In fact, the superficie of Texas is larger than France, for example. And it has a large number of turbines. If you think about it, more than 7,000 turbines have been installed. And on that map, you see a bit the region here in blue where you have wind farms and wind turbines. The percentage of electricity in Texas that comes from wind in 2012 is about 7%. Now, if you think about how many homes can be powered with that, so by the electricity generated from wind in Texas is more than 3.3 million homes that are powered in this fashion. So there have been studies on what are good regions for wind power resources, and it turns out that this region, I mean, Texas is very well positioned, so it's in one of the best places for wind resources. So in fact, if Texas continues to develop wind energy in those regions, the potential is such that it could meet more than 80 times the state's current need in terms of electricity. So the potential is enormous for that. I don't know if you've driven in a region where you have those wind farms, but for example, when you drive from Purdue and you go to Chicago, I mean, it's just amazing. You drive on this interstate and you see wind turbines everywhere. It's very, very impressive. And in Texas, there are some places like this as well. So the data that I'm going to use here consists of hourly average wind speed and wind direction. And in addition to that, I will have information about pressure and temperature at those locations. So I have data for 3 years of data, and I'm going to use the years 2008 and 2009 as training data to train models and fit models. And then I'm going to use the year 2010 as a testing data period. I'm looking at 4 locations here indicated on the map of Texas. And the notation I will use, y is going to represent this wind speed at time t and those 4 locations. And theta is going to be the wind direction at those 4 locations and time t. And what we're trying to do here is to predict the wind at time t plus 2, so 2 hours ahead. At each of those locations, and we'll have a predictive distribution for that. So just a little bit of zooming here to show you what we're doing. So those 4 locations are represented here. They are linked by those 4 red lines. And we have information from other stations, from other locations. Those are meteorological towers. So here we don't have data from the wind farm. It's very difficult to get. You can with some specific agreements and a lot of bureaucracy and things like that, but it's very difficult to get. So those are from meteorological towers. So the ones that are circled here, there are 12 such stations. At those stations, I will have also information about pressure and temperature, and I'm going to use this information to try to improve my forecasts. Here are wind roses of the wind at those 4 locations. So it's for the period 2008 and 2009. And you see basically it's a histogram wrapped on a circle. And you see that, it tells you from where the wind is blowing. So at this location picked here, most of the time the wind is coming from the south, blowing that direction, but sometimes from the north. And different locations have different type of patterns that, of course, you would like to capture in some way. Because if you're in a certain, if the wind comes from a certain direction, then you would think that if you have that information, you can use it to improve the forecast. Here are densities of wind speed, again at those 4 locations for that period 2008-2009. You see that those densities are skewed to the right, and the largest wind speed in meter per second are around 15 or so. So now here are some models that use the information both in space and time to predict wind speed. So, of course, what you can do is the following. So if you have information at a certain location about wind in the past, and you want to predict 2 hours ahead, the simplest way you can imagine is just to use persistence. So you say the wind that I observe currently 2 hours ahead is going to be the same, and that's your prediction. And well, this seems very simplistic, but it's not that bad in some sense. It's not so straightforward to improve on it, certainly at short time scale. But for larger horizon, then you can certainly improve on that. Then the next natural type of model are time series models, so where you use information in the past at those locations, and then you use this to improve your prediction. So typically autoregressive type of models. And then you can further bring information from neighboring location where you have also information about wind speed and wind direction. So a first model that we've developed with Stillman-Knighting is called this RST, or regime switching space-time diurnal model. Essentially what it's doing is that it's using simple regression models on information in the past and maybe a different location, but it uses 2 regimes. This is very specific. So this was done in the Pacific Northwest area. Christy Larson and Westwick were atmospheric scientists that were involved in some wind company there. And the geography, the design was very particular. So essentially, most of the wind were either westerly or easterly, and you had the three locations were a bit aligned in that sense. So most of the wind either came in that direction or from that direction. And there was a wind farm close to that tower here, and so the interest was to predict here. So very naturally in such a setting, you could say, well, because the wind is either easterly or westerly, you divide essentially the direction in either wind coming from there or wind coming from there. And in each of and you decide to switch, for example, based on the wind observed at this location. And so you have two regimes, you have some regression model in those two regimes, and by using that information at another location, you can improve the forecast. And this is what we did there. Now, of course, this worked quite well, but this was very specific to that area. So then we, with Amanda Herring, is a former PhD student of mine now at the Colorado School of Mines, essentially we said, well, why do we have to define those regimes? We could simply use sine and cosine of the wind direction in different locations, put them in the regression model, and so get rid of this somewhat arbitrary selection of the regime. And this is what we did in that model. Then you can play with other kind of ideas. So those models were just looking at predicting wind speed. One other option is to think about the wind vector itself. So not just at its norm. So you look at wind speed and wind direction, but you work in a Cartesian coordinate system. So you can build also some kind of autoregressive model in that setting. And we try to introduce some non-Gaussianity in the distribution of errors based on this QT distribution. So essentially you take elliptical contour distribution from a T distribution, and then you skew it in some direction, and a bit like in the Gauss logo at the very beginning. So you can do those kind of things. The advantage is also then with that model, you can predict wind direction, and you could simulate from that model, and so simulate both speed and direction and things like that. And finally, another version that Xin-Xin Zhu has looked at more recently is to go back to this original model, but say, well, why do we have to just fix those two regimes? We could allow this to rotate or have different type of regimes, so kind of adjust the regime based on some criterion and do something like that. Now, if you look at the performance of all those models, they are very similar. It's very difficult to improve upon them. I mean, if you go from persistence, you can improve with time series autoregressive model. Then you can further improve with those kind of model, but among those four, there's no real big difference. The only advantage of those here is that they don't rely on a pre-decision on the type of regime that you have to use in your model. So for the rest, I essentially looked at those two type of models here. Now, in those experiments in the Pacific Northwest, the information that we had was essentially about wind speed and direction. But of course, those meteorological stations, they collect all kind of information such as pressure and temperature and so on. And so the question is, can you include this into those models and further improve your forecast? Well, you can try to put them just as covariates directly, but if you do that, there's no real improvement as we found. So what we thought is to try to incorporate this information, but from another point of view. So to think about atmospheric science principles related to wind and try to see how this information could be used in the model. So if you look at the troposphere, essentially you have two regions. The upper region, which is often called the free troposphere, and this does not strongly depend on the Earth's surface. And then the PBL, or planetary boundary layer, which has strong interaction with lands and oceans and friction with the surface of the Earth. So this PBL essentially changes through time. This PBL maybe can range from a couple tens of meters to a couple of kilometers. But most of the wind turbines, they operate in this PBL. And the information that we get from meteorological station, they are in this planetary boundary layer. So now what the wind in the PBL is strongly linked to the wind in the free troposphere. And so it seems that if we can understand the wind in the free troposphere, then possibly it can help us in predicting or understanding the wind in the PBL. So this is what we want to do. So in the free troposphere, we can look at what is called the geostrophic wind, which essentially is a theoretical definition of wind that comes from a balance between the pressure gradient force, the horizontal components, and the Coriolis force if there are no friction, because you are in this free troposphere. So in that case, the geostrophic wind is essentially parallel to those isobars of pressure. But now in the PBL, there is friction with the Earth, and so the real wind in the PBL is no longer parallel, it's affected by the friction. And so it seemed that if we could understand or somehow estimate the geostrophic wind, it would give us some information about wind in the PBL where the wind turbine operate. So then you can look at some equation from atmospheric science. I won't go probably in much detail about that, but you can look at what is called the geostrophic equation that describe the gradient of pressure related to, here Z are geopotential height, so essentially gravity adjusted height. And this involves this vector Vg, so Vg represents this vector of geostrophic wind. And so you can work those out, and in fact, what you can do then is to estimate this geostrophic wind from data, from pressure and temperature data at those meteorological stations. So there are different steps you need to do, some correction of bias from possible bias from different observing stations, and so on. So here I skipped some of the detail. I'll give you a reference if you want to look at that. But with those corrections, what we do then is to fit a plane to this computed geostrophic heights at those 12 locations. And then the partial derivative give us the gradient, and essentially then are going to tell us, give us estimates of the U and V component of the geostrophic wind. And then the norm of it would be the speed of the geostrophic wind, and you can have also the direction of the geostrophic wind. So if you look at some data here, you have plots of, in red, the surface wind, so in the PBL, measured from those towers, and then this geostrophic wind that we have estimated through the procedure I just briefly sketched in black. You see that there seems to be quite some correlation between the two. So again, the geostrophic wind, of course, is higher. I mean, it's stronger than the wind in the surface because it's not affected by friction so much. But it seems that if you can understand the geostrophic wind, then possibly you can improve. You have some understanding about the surface wind. And as well, if you look at density plots, in red is the surface wind, and in black is the geostrophic wind, and you see that it has some much larger speeds for the geostrophic wind. You have also daily patterns. So here you have plot at 2 locations, picked and row, 2 of those 4 locations is a function of the time of the day in hours. And the curves in the bottom here are for the surface wind. Those are for the geostrophic wind. They are split by different seasons. So winter is in black, spring in red, and so on. And the dashed one represents an overall measure. But you see that there is some correspondence, and it seems that maybe this could be useful. So the model that we developed essentially it's an extension of this TDD model that I described earlier. But we're introducing now this geostrophic wind as a covariate. So the predictive distribution is a truncated normal distribution. It has a location and scale. The location part is represented like this, so with a diurnal component of this type for different hours of the day. And then the residual part here is the part that is modeled based on both wind speed and wind direction at those different locations, and also at different times, so time t, t-1, t-2, and including also this now wind speed for the geostrophic wind. And the model is, I mean, there's a whole procedure that I won't describe in detail, but essentially we use some version of BIC to select the model in the training period, and then we have a sliding windows that fits the different coefficients and are used to do the forecast. In addition, the scale also is allowed to vary. It's not constant. It changes with some measure of variability here that can be computed. And the coefficient of the model are estimated by this continuous rank probability score, CRPS method that Tillman-Knighting has developed with Adrian Raftery. So here is a table where you have some results for the case of predicting 2 hours ahead at one of those locations picked in 2010 with different models. So you have information for each month of the year, but you have also an overall column about the prediction. The first part here uses mean absolute error as a measure, and the other use this CRPS. So the CRPS is really, I think, the right measure for probabilistic forecast in this setting, but there are many, I mean, once you look at the next step of using this information into a power system, this absolute error plays a role, and so this is also of interest. Now you have different models, so PSS is just persistence. So you say, okay, 2 hours ahead is what I'm observing right now, and the overall MAE in that case is this value here. Now, if you use the RSTD or TDD model that use space-time information, you can reduce this a bit further, but you see those two models are not really very different. But then once you start to introduce also this geostrophic wind, so you have that information from pressure and temperature at neighboring location, you compute this geostrophic wind and you put this in the model, then you can further improve the MAE in this case. And you have a similar situation with the other measure, the CRPS. Now here's a plot that looks at different time horizon. So if you forecast 1 hour ahead, 2 hour ahead, up to 6 hour ahead here, vertically you plot a mean absolute error for those different models. So persistence, you see it, I mean, at short time, it's not that bad, but of course it becomes worse and worse when the horizon becomes larger. RSTD and TDD, the two space-time without geostrophic wind, they are very kind of similar, but they do improve what just persistence would do. And then you have yet a further improvement if you add this additional covariate, which is the geostrophic wind. So if you I mean, this is the end of the first exercise, right? I mean, you do this exercise where you build this model and you try to predict the wind speed, and you see how well you can do that. And I'm sure many of you will have ideas to come up with new models to try and so on, and we can play this game and push it further and further. But you can show those improvements, but then how does this really matter on the power grid? I mean, it's not just the forecast and it's the end of your task. So then the next question is, what's the effect on the power grid? So this is what we've tried to tackle in this part here. So what we've done, we've used a classical kind of reliability transmission system we have adapted it to the Texas region, so to the Energy Reliability Council of Texas, who basically who's operating most of the electricity in Texas with different region. And we've put in different source of energy from wind or coal or gas and so on. And you see that you have different constraints of how the electricity is transmitted, different costs, many constraints, in fact. You can, what we've done then for different type of energy sources, we've given different type of parameters that are somewhat realistic with what is used in Texas. So something about the capacity of the energy source, the cost in dollars per megawatt hour, ramping, so how quickly you can change, as was discussed in the talk on Monday. So you can put all those parameters, and then essentially you have to run a big optimization problem. So what you're trying to do is to introduce different sources and different quantities of power in that grid. So you have a big optimization problem, and I will not describe everything in detail, but essentially you're trying to minimize the cost of running this power grid under all kind of constraints. We have to balance the demand and what can be produced. And then you have ramping constraints, you have all kind of cost linked to operating this power grid, and you can also look at the worst case scenario and so on. And so this is what my colleagues in electrical engineering have been running with the input of the wind forecast from different models. So we've used this space-time model that I described that included the geostrophic wind. And overall, what we've seen is that we can reduce the generation cost and running the grid by up to 6%. This seems like a very small number, but if you think about the amount that are involved here, essentially you're talking about tens of millions of dollars annually in region where you have a lot of wind penetration, for example, like in Texas or the Pacific Northwest, or I'm sure in many other regions. So we have two publications related to this effect on the power grid. There's one that is coming up in the Spanish journal Test. I wanted to have a publication in kind of a European journal with some discussions. That one focuses on the application in the Pacific Northwest, and the other is in the IEEE transaction on smart grid, and this one focuses on the application in Texas. And of course, another question of interest is to integrate also solar power. I haven't talked about that, but this is another question that also is of interest. In Saudi Arabia, there are not too many clouds, so most of the time it's sunny, but you have all kind of dust and problems with the solar cells, so there are the issue of that type. In other regions of the world, there are a lot of clouds or rain and so on, so then you have to kind of understand how much power you will get from the sun. So here's a summary of some of what I've discussed. Essentially, some of those short-term space-time probabilities model to forecast wind. I've described this idea of introducing the geostrophic wind to improve the forecast. And in fact, the improvement that we got just on the wind speed in terms of compared with persistence. Also, I didn't describe here, but we did this at different location, range between 14 and 22% improvement. And compared to other space-time model that did not use the geostrophic wind, we got another 5 to 8%. This again stops at the level of forecasting just the wind speed, but then is the question of how does this improve the power system dispatch and optimization there, and there are some improvement, of course, in there as well. Now on Monday we had this discussion about ramping events, and I think this is also another thing that is interesting to pursue in this setting. I think this question of the definition of ramp event, we've seen there are many existing definitions, how we predict those and so on. I mean, it's not completely trivial. There was some proposal in the talk on Monday. And then is also the additional step is if you can improve prediction of those type of events, how you can change the operation of the power system and evaluate those improvements with the power system, as I did just on the forecast. So I think here there's another direction to explore. And I wanted to mention here the paper of my former student who recently looked at trying to forecast categorical changes in wind. So either an increase of wind, a decrease, or just a stable case with some kind of simple models. And I wanted to put it here because if the speaker from Monday gets the slides or other, there's this reference here as well. Now there are some other opportunities to pursue, I think, related to the change point here. One question that we've already tried to explore is to think about whether climate change might have an impact on diurnal wind power cycle. So those wind farms, typically they're designed to last many years, and if the climate is going to change, if the wind patterns maybe will change, then how will this affect production of energy from wind? So what we've done with Steve Sain at NCAR and so Maddie Herring at Colorado School of Mines and Scott Goddard is a current student at Texas A&M, is to take information from climate models. We're looking at 12 locations in North America. We have 9 high-resolution regional climate models, and we have 2 periods, essentially a current or past period if you want, and a future period. And we try to look at differences between the current period and the future period. And we developed some testing procedure for that. You can do it in many different ways, but what is interesting is that we detect some significant changes at certain location. And what is interesting then is to look at the change in terms of amplitude or shape or position of those cycle that may have an effect on how much power can be generated at those wind power. So here I have some plots of the 12 different locations split for different seasons, summer, autumn, winter, and spring. And essentially those points, the darker they are, the more significant the change is. And you can see that there are some regions, for example, in the winter on the west coast, it seems there will not be too much change. But there are some other locations, for example, this one near Cape Cod, where there is this big discussion about wind farm there, that does not change essentially most season except in the summer. And you can then look at this change and try to see whether there will be changes or not. So I think here there's, maybe some further exploration that could be done in terms of, if you have data about wind, can you detect changes in time, and how will this affect the wind energy sector and so on? So there is maybe a link to that here. Okay, so how is time? Just a few.
Couple more minutes.
Okay, so here are some other projects that I've started to look at with my former colleague at Texas A&M. One of them is exactly this question of, you don't have really the theoretical curve. This is not really what you get. So how can you cope with this variability in the relationship between power and speed? So we've developed some model where there as well we use additional information to try to adapt the power curve to different environmental setting, environmental factors, and see how this can lead to further improvement in terms of predicting wind power. I've put also a list of the paper that I've written on the topic, just so that they are in the slides if somebody wants to look at them, and you can download them from my webpage. There's now old review here in significance. There's another review that we wrote, that we published in 2012, which also talks about power system operation. And now there's a new paper by Pierre Pinson in statistical science that also is the most recent one about statistics and wind energy. And then the other papers are related to those different models that I've described. So I have two brief previews before I end here, coming very soon to a seminar room in your neighborhood. So the first one I think is quite exciting. Stefano Castruccio is a postdoc in my group, was a student of Michael Stein in Chicago. And essentially we're looking at three-dimensional climate model output, temperature on Earth. So you have also altitude on Earth, which is not represented here. And this is what has been created at a certain altitude from climate model. It basically takes 6 months to get that output. Now we're emulating this with a space-time climate, space-time statistical model on the Earth, three-dimensional on the Earth, and we're fitting this model to 1 billion data points. So this uses spectral techniques on one band first, and then stitching the band together on the surface of the Earth, and then adding the layers for the third dimension. And at KAUST, we have a visualization cave in 3 dimensions, and we're developing visualization technique for the data and the emulation in 3 dimensions. So this is something that maybe some of you will be interested in. And another one is about visualization of surfaces and images. We have a paper that comes out in STAT very soon. It's called Surface Box Plot. And what we do is here we have a set of brain images, and we can rank them. So we can sort those images from the deepest in the sample to the most shallow, most outlying. So this is the median image. It's a true image in the sample. And then we have a kind of 3-dimensional box plot where we can look at those images. We can extract unusual images. So some on the left here are unusual compared to, for example, the median here, and you see certain patterns that are unusual. You have plots of the depths of each image in your sample. You can click on a certain point, and then you have the image that comes here. You have also a histogram of the depths. So this is another tool that I think might be of interest to explore with. So those are previews. I don't say more about that. And this is my previous slide, my conclusion slide. So I think I stop with this, and if there are any questions. Thank you.
Questions, comments at all?
Can you explain a little bit how you use the geostrophic wind once you calculated it in the space-time model?
So what we do is, okay, maybe I'll just go back to that model here. So for example, here we're trying to predict the wind 2 hours ahead at one location here picked, one of those 4 locations. So we can compute the geostrophic wind at that location at the current time and at previous times as well, T-1, T-2 here. And basically those are used as predictors in the model. Now how this wind speed is, this geostrophic wind speed is computed is with this procedure that I kind of just sketched out. So you use information at neighboring station, you do this adjustment of the plan and some kind of tweaking to remove potential bias and some kind of adjustment of this type. But then we use this as predictors.
I wonder if you could give a comment just on how you actually incorporated the forecast and the confidence interval for the forecast into the power system modeling.
Yeah, so it's somewhat complex.
I can imagine.
So, I mean, basically the forecast gives an upper bound on how much is expected to, that can come from wind. So it gives an upper bound on how much could be taken in the optimization from wind. And then what we use in this version is some measure of the confidence interval that gives some kind of, how should I say, some kind of buffer in the optimization. But in fact, I think more can be done on that. And I think in the review by Pierre Pinson in that article, he talks a bit about this, that I mean, we're not really using the full probabilistic distribution. I mean, I think the main ingredient is the point forecast, and there's a little bit of this buffer from a confidence interval. But I think there's room to have a more kind of probabilistic optimization where you have information about the forecasting distribution, the predictive distribution, and use all that in some way in the optimization. But this, I'm unaware of result on that, or maybe you or others are doing, I don't know.
If I'm a power company and I want to decide where I want to put my wind farms in the world, and I've been given some kind of cost function as to how much it'll cost if my output is constant, if it's this variable, can I figure out where I want to locate it to maximize that cost function? So I've got my space-time distribution.
Yeah, this is a very, very difficult question, as you can imagine. I mean, the model that I have described here, they use spatial information, but they are not spatial in the sense that I'm not predicting at a new location. So I'm not interpolating through space, right? So I think if you want to answer those kind of questions, first you have to look at models that really are fully spatial. And then, I mean, it's a bit question of network design in some sense, tailored to that particular problem. I think it's a complex problem in general.
But depending on the region you're in the world, you may own a percentage of one wind farm and a percentage of another, and then there's a portfolio question there about how do you create your portfolio to
but I think you could run climate models or things like that, different scenario and kind of sea region with a lot of wind and thing of this order, but
I mean, my impression is that when people are trying to forecast, they're trying to forecast for one wind speed at a farm.
right.
But at the same time, I've heard wind engineers tell me that if you've got an array of towers, depending on where that wind hits, it's good, you get more wind at the front.
Yeah, there are some very complex effects on.
Do people look at the effects?
I'm not sure. At least we did. I mean, we completely ignore that. But it's clear that there are physics on. I mean, if you have a turbine here and one behind, and the wind is blowing like this, or even nearby, I think in the back there's some kind of effect like that, and it's. I mean, it's a complex. Yeah.
So when you're doing the comparison with the analysis on the climate models, obviously when they're creating these scenarios for the climate models, they're actually putting in different scenarios going forward. Did you compare the results that you were getting for the increase or decrease and significant changes in the wind with what the actual parameters were for the actual simulation?
No, so I think we looked at, one scenario, which is about A2 or something like that, one of those not too bad, not too good scenario, but you're right. I mean, one could play with all kind of things there. I think there's really an area of problem that could be tackled towards.
I mean, when they're creating these, they're actually saying, okay, we're going to have more of this or less of this when they're putting the parameters in. So it'd be interesting to see if the results from your model actually match the fact that the scenario you were looking at was an increase in wind in the wind. Obviously, it's a bit more complicated than that because there's not a direct parameter for the wind. But should be able to.
Okay, so let's thank Mark for his main talk.
No, that's the only one.
And we'll take a mini break so that those that need to leave